Thanks everyone for having us. We're excited to be presenting ExoFlow. So first, what do we mean by a workflow? Well, a workflow is a pipeline of different applications that's meant to be executed together and in some specific order, often specified through a DAG. And this has become an important pattern recently as distributed applications are becoming more diverse. So let's take a training workflow as an example. Now, this might sound like it's just one application, but actually it can be composed of multiple distributed steps. For example, we might have an ETL job, which produces a preprocessed data set, an online data processing step to augment the data, and then finally we feed the augmented data into a training job. Now, each of these tasks might actually involve a separate distributed system. And to coordinate these systems together, today developers are using workflow systems such as Apache Airflow. And the primary role of this workflow system is to provide automated scheduling and failover to reduce user burden. Of course, we want performance, which in this case means scalability with the cluster and the DAG size, and low enough overheads for the application. What applications do we mean? Well, last but not least, we also want the system to be general, because we want to interoperate with arbitrary application code and third-party systems. This kind of system is being used in other domains too. For example, workflows are becoming popular for serverless execution because they make it easier to execute complex applications. So here's one example where we use a serverless workflow to atomically reserve a hotel and flight for a web app. The granularity of execution here is, of course, very different. And indeed, today we have completely separate workflow systems for serverless versus data workflows, but we still want many of the same system properties. But the problem is that these applications are very different, and it's not just because one is serverless and the other one isn't. One of them is also offline, while the other one is online. One is idempotent and deterministic, while the other one affects and depends on external state. And these differences matter for failure recovery, which is one of the main responsibilities for the workflow system. In general, recovery techniques follow a trade-off between execution versus recovery overheads. For example, Apache Airflow uses checkpointing, which is great for an offline data processing job. But checkpointing may not be practical for an online workflow that interacts frequently with the outside world. And that's why recent serverless workflow systems often use logging and replay instead. So what we see is that because of this trade-off, current workflow systems end up choosing one point on this trade-off space. And so we end up with different workflow systems for different use cases. In this talk, we're going to make a case for building a universal workflow system that can enable a flexible choice over this trade-off. And so the key idea is to decouple the unit of recovery from the unit of execution. In other words, the user will still define their workflow as a DAG of tasks, but now we want to decide how to recover each task independently, using potentially a different point in this trade-off space. And to do that, we need more application semantics. So let's take a look at some examples to understand what we need. The standard correctness requirement for failure recovery is to provide exactly once semantics. And informally, this means that the output of the workflow should match some failure-free execution. So let's take a look at what kind of output a workflow can produce. In our model, a workflow is going to be a DAG of function calls, or tasks, and each task here can have two different kinds of outputs. A task can directly return a value, and we call these values internal outputs because they get passed to other workflow tasks. A task can, of course, also interact with the outside world, for example, with a key value store. And we call these external outputs because they can be viewed by processes outside of the workflow system. For exactly one semantics, we want both the internal and the external outputs to all be consistent with a failure-free execution. Now, the challenge here is that these tasks can do arbitrary things. So the tasks might be non-deterministic, and they might have arbitrary external outputs. Under these assumptions, the only safe thing to do here is to require external outputs to be idempotent and to synchronously checkpoint a task's outputs before we begin the next task. And to see why that is, let's take a closer look at what happens if we don't do this. So if we don't synchronously checkpoint, let's suppose here that A is non-deterministic and B completes, but then C fails. So if we don't have a checkpoint for A's output, then we have to go back and retry both A and C, like this. But of course, this is going to conflict with B's previous output. And here, the good thing is that since this output is internal, we can roll it back just by dropping the previous value for B and rerunning B along with A, like this. But that's not necessarily possible when we have external output, as we do here. There's no single way to roll back an external output, and in many cases, it may not even be possible to do that correctly. So if we want to protect against this case in general, then we have to synchronize this checkpoint for A's output before we execute B. And so to summarize, current workflow systems assume the worst about task semantics. And that's why they have to synchronously checkpoint these outputs before executing the next task. And this strategy is simple and correct, but it's also unnecessary depending on task semantics and potentially expensive, especially if the data is large. And so that brings us to ExoFlow, where we want to decouple the unit of recovery from the unit of execution. Now, how are we going to do this? Well, our solution has two parts. So first, we're going to expose task semantics to the system using annotations for non-determinism and external outputs. And that way, we can avoid unnecessary checkpoint synchronization. The second part of our solution aims to reduce the execution overhead of recovery in general. And to do that, we're going to allow workflow tasks to pass internal outputs by reference instead of by value. And that way, we can avoid unnecessary materialization and copying. So these steps towards decoupling the execution and recovery units is what differentiates ExoFlow from current workflow systems. Some recent systems for flexible recovery have also tried similar ideas. And the main thing that ExoFlow is adding here is the use of references and annotations. So let's take a look at these in more detail. First, we'll show how references can make data passing more efficient and flexible. A workflow system like Airflow materializes task outputs and checkpoints before downstream tasks begin. So that means that B and C here will each get a copy of A's output, which of course is unnecessarily expensive. Our solution is to use references. Instead of returning a large output by value, a task can return a reference. And then the execution backend can decide how to actually pass the value to the consumers. For example, here, the actual data for this reference could be shared through some external store. Next, let's take a look at how task annotations can help reduce the execution overhead in the serverless transaction workflow that we saw earlier. So some existing workflow systems for serverless handle external outputs by providing idempotent APIs. And that way, each task can be safely retried if it fails. But we still have this problem where tasks might be non-deterministic. So we have to make sure to record each task's outputs before downstream tasks can start. It turns out that we don't actually need to do that to achieve exactly one semantics. So let's instead try to treat the external state as a black box and just look at each task semantics individually. So let's say here we're using a two-phase locking protocol. And the first task is going to return a non-deterministic transaction ID, which we can pass internally to the reserved tasks. Each reserved task here acquires an external lock and then does an update to reserve the hotel or flight. So these tasks do have external outputs, but they can also be rolled back. And that means it's actually safe to skip this checkpoint or make it asynchronous, as long as we roll back any external updates on failure. And that's pretty simple to do here just by aborting the transaction. On the other hand, if we commit the transaction, we can't roll it back anymore. And so here, when we have non-deterministic inputs, it means that we have to synchronize this checkpoint before we begin the next task. But one more trick we can play here is to overlap that checkpoint with other tasks. So to do that, we split the reserved task, one task to acquire the lock and one task to apply the update. And the update task here is actually deterministic, and it doesn't have any visible external outputs because we're still holding the lock. And so we can actually delay this checkpoint as long as we synchronize it before the commit or abort begins. By giving these semantics to ExoFlow before execution, the system can decide when to synchronize checkpoints during execution. So next, I'll hand it over to Siyuan to present the architecture.
Yes. So thank you. Yeah. So the architecture of ExoFlow is straightforward. Our main goals are to be able to scale recovery and execution independently and to make the backend pluggable. The storage layer contains the workflow task description and checkpoints for task outputs. The workflow controller is implemented as a rate actor that can be scheduled by workflow ID. It caches a copy of the DAG in local memory and coordinates the task execution and the recovery. The executors run tasks and write checkpoints to the storage. They are implemented. These executors are also implemented with reactors, but they can also delegate execution to a different backend, as long as this backend supports remote function execution. For example, we provide an AWS Lambda backend for serverless workflows. Now, let's see how this works in practice. Our first experiment mimics an ETL pipeline where a Spark job produces data read by multiple consumers. This application is intentionally simple because we just want to measure the overhead of data passing. Our goal is to show how a developer can use references to pass task outputs efficiently. Remember that Airflow task has to copy the data in order to pass it. Since there isn't enough memory for consumers here to run with their own copy, performance gets worse with more consumers. Instead, if we use ExoFlow, one can pass the Spark RDD by reference, and all the consumers share the same physical copy of the RDD. This, of course, matches the performance if we run the whole workflow with Spark. So here, the benefit of using ExoFlow is that we can also orchestrate the Spark job with other downstream applications that aren't using Spark. The second experiment looks at a serverless microservice workload. This benchmark includes the trip reservation that we saw earlier and a mix of other queries. We compare against Berkeley, a recent serverless workflow system. Here, we see that without failures, we can achieve up to about 50% lower P99 latency than Berkeley. This is because Berkeley uses white-hat logging for all tasks in the workflow. But many of the workflow tasks here in the workload don't need such a heavyweight recovery technique. By adding some annotations, we can get much lower latency with ExoFlow. That explains the reduce of the P99 latency here. The performance with failures is also about the same in ExoFlow. That's because we use a centralized controller that can quickly detect and retry any Lambda failures. Berkeley uses a decentralized design, which makes it completely serverless, but it also makes it more difficult to reliably detect failures, so its minimal recovery time would likely to be in the magnitude of seconds. Let's zoom in the trip reservation workflow that we saw earlier to see how ExoFlow annotations can help even more with performance. We first show head-to-head results for the sequential workflow used in Berkeley. We can reconstruct this workflow to run the hotel and the flight reservations in parallel instead of sequentially. And finally, we can further break down each reservation into two tasks, like we saw earlier. This by itself, as the figure shows, doesn't change the performance, but if we combine it with ExoFlow's asynchronous checkpointing, then we can overlap the checkpoint with the updated task, so to get a reduced latency. So please Here's only part of our results. For full results, please see our paper for more information, including results on a more diverse set of applications and a more complete discussion of our system design. So in conclusion, we show how ExoFlow decouples the unit of execution from the unit of recovery. We use this to enable flexible trade-off between performance versus recovery for workflow applications. Please feel free to reach out with any questions. Thank you.